Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. This week on the podcast, we're featuring a series of conversations from the AWS reInvent conference in Las Vegas. I had a great time at this event, getting caught up on the new machine learning and AI products and services offered by AWS and its partners. If you missed the news coming out of reInvent, and want to know more about what one of the biggest AI platform providers is up to, make sure you check out Monday's show, TWIML Talk number 83, which was a roundtable discussion I held with Dave McCrory and Lawrence Chung. We cover all of AWS's most important news, including the new SageMaker, DeepLens, Rekognition video, transcription service, Alexa for Business, GreenGrass ML inference, and more. In this episode, I'll be speaking with Nikita Shamganov, co-founder and CEO of MemSQL, a company offering a distributed, memory-optimized data warehouse of the same name. Nikita and I take a deep dive into some of the features of their recently released 6.0 version, which supports built-in vector operations to enable machine learning use cases like real-time image recognition, visual search, and predictive analytics for IoT. We also discuss how to architect enterprise machine learning solutions around the data warehouse by including components like data lakes and Spark. Finally, we touch on some of the performance advantages that MemSQL has seen by implementing vector operations using Intel's latest AVX2 and AVX512 instruction sets. And speaking of Intel, I'd like to thank our good friends over at Intel Nirvana for their sponsorship of this podcast and our reInvent series. One of the big announcements from reInvent this year was the release of Amazon DeepLens, a fully programmable deep learning-enabled wireless video camera designed to help developers learn and experiment with AI in the cloud and at the edge. DeepLens is powered by an Intel Atom X5 processor, which delivers up to 100 gigaflops of processing power to onboard applications. To learn more about DeepLens and the other interesting things Intel has been up to in the AI space, make sure to check out intelnirvana.com. Okay, just a couple more quick announcements. You may have heard me mention last time that over the weekend we hit a very exciting milestone for the podcast, 1 million listens. What an amazing way to close out an amazing year for the show. It occurred to us that we'd hate to miss an opportunity to show you some love, so we're launching a listener appreciation contest to celebrate the occasion. To enter, just tweet to us using the hashtag TWIML1mil. Every entry gets a fly TWIML1mil sticker, plus a chance to win one of 10 limited run t-shirts commemorating the occasion. We'll be giving away some other mystery prizes as well from the magic TWIML swag bag, so you should definitely enter. If you're not on Twitter or want more ways to enter, visit twimlai.com/twiml1mil for the full rundown. Last but not least, we are quickly approaching our final TWIML online meetup of the year, which will be held on Wednesday, December 13th at 3 p.m. Pacific time. We'll start out by discussing the top ML and AI stories of 2017, and then, for our main presentation, Bruno Gonçalves will be discussing the paper Understanding Deep Learning Requires Rethinking Generalization by Shiyuan Zhang from MIT and Google Brain and others. This will be a fun meetup and one you don't want to miss, so be sure to register at twimlai.com/meetup if you haven't already done so. And now, on to the show. All right, everyone. I am on the line with Nikita Shamganov. Nikita is CEO and co-founder of MemSQL. Nikita, welcome to This Week in Machine Learning and AI.
Thank you. Thank you for having me.
Absolutely. Nikita, why don't we get started by having you tell us a little bit about your background? You are the CEO of MemSQL, but you've got a pretty technical background. Isn't that right?
That's right. So I'm a PhD in computer science from St. Petersburg, Russia. And I moved to the States to work on Microsoft SQL Server, which I did for a number of years. So I have a very strong database and query processing background. After that, I moved over to Facebook, where I was blown away by the magnitude of data problem Facebook was solving back then. And since they only increased in magnitude. Seeing that and combining the visibility into those workloads and kind of making that assumption that in 5 years, a lot more companies are going to be facing those challenges just like Facebook, I decided to start a company and combine that database background and expertise of building systems. And the early stages and the glimpse of the workloads that I saw at Facebook, so I kind of knew where the world was going into. So that triggered my desire and gave me some insights into starting MemSQL, the company. So we've been at it for 6+ years, and certainly validated some of the assumptions we had starting that journey.
So I've come across MemSQL, and I think of the company as an in-memory database. Tell us a little bit about what the focus is there, and in particular, what's the intersection between what you're doing and machine learning and AI? Are you seeing a lot of those types of workloads nowadays?
Definitely. That's certainly where our customers are moving towards. But let me step back for a second and talk about MemSQL and in-memory database and the technology.
Okay.
We started as a purely in-memory database. And then since we've evolved to support a large class of applications that are built on top of MemSQL. And in-memory became an enabling technology, but it's not the technology at MemSQL. As a matter of fact, the key advantage that MemSQL brings to the world is the fact that it supports SQL, which is a structured query language, and the fact that it runs the database in a distributed environment. So you can run MemSQL on your laptop, or you can run MemSQL on 1,000 hosts. That gives you an immense compute power to enable the new class of applications. So let me talk about what kinds of applications we support. Certainly some of them have to do very little with AI and ML, and MemSQL enables scale, latency. You can build very low latency applications on top of MemSQL, and that's where in-memory technologies come handy. And you also can build applications that require very high levels of concurrency. And that concurrency is enabled on top of the system of record. So MemSQL supports state, and it supports full durable persistence. SQL also allows you to build what we call real-time applications. And kind of the idea of real-time applications is the opposite of batch. So every time you need to do analytics and you do some sort of pre-calculations upfront using Hadoops or data warehouses or any other offline and batch-oriented technology, that's basically our enemy. So we're bringing the world to be completely real-time and perform all the computations that you need to live. And we deliver it on extremely low latencies by leveraging an immense amount of compute. And that we can do very, very well because MemSQL is a scalable technology that can run on clusters of commodity hardware. So now where AI and ML comes in, well, because we support this new class of applications, the fact that our customers are incredibly forward-looking, they want to do more with the technology, and they want to blend classical database workloads with the new types of computations that are mostly stemmed from the AI and ML needs. And one of the big ones that we see all the time is image recognition. So we can talk a little more about it. So let's say you have an application and you use that to power, and you use MemSQL to power that application. The application is large scale. There's a ton of data that's stored in MemSQL. Like I said earlier, in-memory is an enabling technology, but it's not the technology. You can actually put a lot more data into MemSQL than there is memory on the cluster. And what you want to do is you want to enable smart applications, the ones that make decisions on either on behalf of a user, or they provide recommendations, or they provide some sort of search capabilities on top of unstructured and semi-structured data. Imagine an app that has a camera. It runs on your cell phone. You snap a picture with this app, and just in a few tens of milliseconds, this app finds similar images to the one that you just took a picture of. So why is it useful? Well, it's useful because you just enabled visual search. And the way we do it is we built some of the building blocks that allow you to run and operationalize the machine learning models, and we build them straight into the database. And now the database allows you to scale them and deliver very low latencies for this type of operations. So that would be one example of an application. I can give you another one, which we see a lot in the IoT space.
Before we go into the next example, can you drill down a little bit into what specifically MemSQL is doing to enable the first example? For example, are there pre-trained models, for image recognition or image similarity in this case, built into the database, kind of like, you might think of a stored procedure, or is it, is there something else? Is it a different type of functionality?
Yeah, it's even lower level than that. MemSQL certainly supports stored procedures, but in this particular case, we implemented a few building blocks, particularly dot product and Euclidean distance between vectors.
Oh, that is pretty low level.
Yes, and if you take a deep learning model and you look at the layers, matrix multiplication, tensor multiplication, vector multiplication is the fundamental building block. Mm-hmm. So what we do is, as we train that model, we take all the layers except for the very last one and apply it on the database of images that we have. And that allows us to extract what we call, or anybody else calls a feature vector, which mm-hmm. is just a vector. So once we have that and we have a model, applying that model to an incoming image, which you just took a picture of, with your cell phone, will produce another feature vector. And it just so happens that the multiplication of those two feature vectors normalized gives you the similarity score, how close those images are together. So the heavy lifting of building a model belongs to somewhere else. And the data might as well be still stored in MemSQL, and we enabling very fast data transfer in and out of MemSQL in a parallel way. So we can send it into Spark or TensorFlow or any other training framework. But once it gets to operationalizing that model and performing the last mile computation by really powering your app, then MemSQL gives you that scale, and it allows you to perform those computations pretty much at the memory bandwidth speed. That enables really low latencies for that last mile computation.
Okay.
Does it make sense?
Okay. And no, it does. So you're computing these feature vectors. Is that happening on write of new images, or is it happening? I'm assuming that's the way you would do it, since you're anti-batch. You're not doing some big batch job that's like updating, some column in your database with your feature vectors for all the images that are in there.
Correct. And you can do you can do either, but the typical workload is once you have that model, you're applying that model on write. And we have technology, it's called pipelines, that allows you to perform arbitrary computations, either in a stored procedure or an external piece of code. That's where you can invoke all third-party libraries to apply that computation and then store the feature vector in the database. So you can do it in ingest, and if let's say you build something like you crawl the web or you crawl your own product catalogs, and once you identify those images, you immediately stick them into the database. As you do that, we trigger that computation. So the feature vector arrives into the database at the same time, instantly, as the actual data. And now it immediately participates in all sorts of computations. So that allows you to never have kind of stop and go computations. You never do, step one, load all the data. Step two, perform the batch computation on top of all the data into the database. And step three, do something else with it. Rather, it's all streamlined and it just flows in and out.
And so how does this play out in the IoT case?
So in the IoT case, data is incoming constantly. So one of the use cases we have with a large energy company is to ingest IoT data from drill bits. Apparently, in the world of fracking, you tend to drill a lot more, and then there is a non-trivial cost for a broken drill bit. Now, those things are extremely expensive. You have to stop your operation if a drill bit breaks. So you're losing of not only on the fact that you're fishing this thing out from the ground from hundreds and or maybe even thousands of miles deep, but you're also not producing oil, which is an operational cost. So what we do, we ingest that real-time data, IoT data, and we're scoring that data, applying a machine learning model in real time. And then there's an application built that arrests the drill bit before it hits a problem, just by measuring temperature and all the very, temperature, throughput, all sorts of kind of vital signs of the drill bit as it goes through the ground. And so that was step one. And step two is obviously you feed all this information back to direct the drilling. So in the world of fracking, drilling is directional. So it's not just vertical down into the ground, but it's more like you're changing the direction as you go and drilling. Right. So using all that input, you can direct the drill bit to make the whole operation a lot more efficient.
And what are some of the algorithms that come into play in that use case?
So they started with, like every typical data science, they started with some sort of linear regressions. They moved it to decision trees very quickly. And now they're experimenting with deep learning for that as well. And the beauty of that of the solution that we presented is it integrates natively with all sorts of third-party libraries. So we made the experimentation for them very, very straightforward. They started with SAS, where they produce models in SAS. As you know, SAS is a proprietary technology. But since they've played with Spark and now experimenting with TensorFlow as well.
Okay. I was actually going to ask you about Spark and how that fits in with your model. I imagine you see it out working with customers. Is it a competitive technology, Spark plus the rest of the Hadoop ecosystem, or is it complementary, or how do you see that?
So all the big data technologies overlap a little bit. In the case of Spark, I would say it's 90-10. So it's 10% competitive and 90% complementary. And here is why. Spark doesn't have state. The state is usually stored somewhere else. It's either HDFS, a relational database, or S3, some sort of object store in the cloud. So what we do in this case is we provide an extremely performant state. And the combination of MemSQL and Spark, that's the 90% case. They work really, really well together because we give you that transactional, scalable state. And nothing else on the market can give you that state. So not only you can store, you can retrieve, but you can also compute. And we have a world-class SQL query processing engine that allows you to produce reports, but also allows you to modify that state in a transactional fashion. You can say begin transaction, insert, update, delete. You can run it at high concurrency, and you have full durability and all sorts of guarantees for that data. So that's where we're extremely complementary. The typical deployment model is that there is a data lake, and that data lake stores hundreds of terabytes or petabytes of data. MemSQL is deployed alongside of the data lake to power applications, because you cannot write applications on top of Hadoop because Hadoop is batch. So now, and then Spark is the glue between those two, and it allows you to have rapid data transfer. All the data that is born in MemSQL based on the interactions with applications. That data is captured. You can pick it up in Spark very, very easily. We have a world-class Spark connector. Drop it in the data lake for historical, archival, compliance type storage. and then perform some overnight batch computations, take the results of those computations, stick it into MemSQL, and Spark oftentimes give you that unified API, because through that API you can interact with MemSQL, you can interact with the data lake, and that becomes kind of the go-to API for application developers. And MemSQL in this case just gives you SQL. Then you can attach a BI tool directly into MemSQL, and then you can scale the concurrency of data scientists that attach their BI tools to MemSQL and look at the reports and visualizations.
And is it primarily data scientists and folks that are and kind of end user use of MemSQL, or are you also in this scenario attaching your traditional applications to MemSQL, or are you using some other state technology for building applications that refer to this data?
Well, mostly it's actually application developers, because MemSQL powers applications, and because the nature of applications is changing all the time, and we have higher scale requirements for the applications, MemSQL is a perfect technology to power applications like this. I'll give you a few more examples of such applications. Now, because modern applications have AI and ML requirements, that's where that intersection comes in, where you need to have those models and that you produced somewhere in your data science lab, and you want to operationalize those models. And that's where MemSQL plays very, very strongly.
So do you envision, kind of along the lines of what Spark's done, kind of building higher level abstractions beyond dot product and Euclidean distance to enable folks to do machine learning and AI more easily?
Oh, absolutely. Absolutely. We have a number of ideas that are circulating inside the engineering team, and certainly influenced by our customers and what they want to do as a technology. What the customers see in MemSQL is that very, very fast, scalable state that they can deploy inside their data centers or in the cloud on the cheap, right? Because MemSQL provides world-class compression, it has column store technology, and that state is very fungible. Because we support transactions, you can change that state, you can enrich that data with attributes that you compute on the fly, et cetera, et cetera, et cetera. Now, what people want to do is they want to perform computations that are beyond SQL. So we're world-class in SQL query processing, and that's great. And our customers want to do that and more. And when they want to do more right now, we resort to Spark, right? We say, okay, well, deploy Spark alongside of MemSQL, pull the data out, and we'll give you that data very quickly, perform the computation, put that data back, and then leverage some of the building blocks that we have, basic arithmetic operations, vectorized operations, vector operations, to do the last mile computation to power your applications. Now, once you do that, you just want to take that loop and you want to tighten it up. So you start bringing all the computations that you're taking data out of MemSQL, put it somewhere else in a temporary store like Spark, data frames, and you want to perform those computations in place. And there are two interesting problems in that space. One is what the API should be. And today for machine learning and AI, the APIs tend to be either Spark-driven or the Python library ecosystem driven, the likes of NumPy, SciPy, Pandas, TensorFlow. So it seems like the Python world lives in one universe, the Spark world lives in another universe. And then there's the SQL universe that is pretty much ubiquitous because every database exposes SQL as an API, and also data warehouses expose SQL as an API. Our view that the Spark universe and MemSQL universe should be enabled by rapid data transfer between the two. And then the Python universe should be enabled by pushing some of the computations that you express through Python API into the database and putting them on steroids.
Now, what exactly does that mean? And can you give an example?
Yeah, totally. So let's say you performing a non-trivial computation on your data. Let's say you have 100 terabytes of data. Certainly more data that can fit on your laptop, and you're a data scientist. And as a data scientist, you live in the Python world.
Mm-hmm.
And you're a big expert in the libraries like Pandas, NumPy, and SciPy, and let's say you're playing with TensorFlow as well. So it's very natural for you to express computations on that data to perform training or perform scoring on that data in that Python world. The problem is all the computations are single-threaded, and all the computations are in memory. So you're stuck at this point in time because you cannot access 100 terabytes of data because there's no way you can put 100 terabytes in memory. And that's where we see the world is going to, where you want those computations to become instant and parallelizable and scalable, not so you can just, instead of bringing that data into your high memory machine, you can perform those computations in place in something that's very, very scalable, like MemSQL. So you're going to see more and more of that happening over time.
You mentioned the three different kind of modes of interacting with this for machine learning or in general, Spark, Python, and SQL. Are there any efforts to extend SQL to give it some kind of machine learning expressiveness? Like, SQL's got, all kinds of aggregation operations like select average of X, where, whatever, right? I can imagine, something like, select predict, Y, where, whatever, where you're kind of expressing in SQL that you want a prediction, based on something. Does that exist? Are folks playing with that today?
Yeah. So if you look at the history and you look at products like, good old products like Teradata or Nikitas, or if you look at SQL Server integration with R, that's certainly something that is happening, where training is not happening in the database, but scoring is. That's a natural way to do things. We achieve the same functionality through pipelines, where we score data on ingest. Okay. So I think this is valuable, and you'll see databases exposing more and more primitives, the likes of dot product and Euclidean distance, but you'll have, instead of 2, you will have 100 of those built into the database. And then you will see packages where it's just a package of stored procedures which allows you to run those predictions. And those will work really well for simple use cases. Now, if you look at the world of a data scientist today, they actually don't like that. They like to live in the world of data frames, where there's a lot more control over the types of computations that people are expressing. People understand that world of data frames very, very well. So I think the future is going to be actually in parallelizing and speeding up computations inside data frames. So that's just my opinion.
Do you envision doing training directly in the database?
In the same way as I described the interaction with the data frames. So if you want to enable inference in the database, then you don't want to have the database to be a crutch where you're constantly fighting and trying to shoehorn that computation into SQL. The natural way to expressing those computations is operations on top of data frames. However, if you make the database naturally support those data frame computations, then you have tremendous value from the fact that the database actually owns the state, and you never need to transfer that state from your storage to something else. So you're bringing computations closer to data. So that's where I see the industry is moving in the next 5 years.
You just mentioned bringing computations closer to data, and that's obviously been one of the things that the Hadoop ecosystem has made more readily accessible to folks. This idea of data locality. Do you get to take advantage of that with machine learning types of models in general and this pipelining approach that you have in particular, or are the pipelines run, outside of, separate from any concept of locality of data?
Well, locality is a loaded concept, right? So you can start with, okay, well, I want to perform computation exactly on the same machine where the data is stored. So that's kind of the extreme case of locality. Another way to think about is, as you look at the computation plan, let's say in the database terminology, there would be a query plan. So let's extend the definition of a SQL query plan to a broader concept of you performing some sort of arbitrary scalable computation, and you know all the steps in the computation up front. So you can optimize those computations and produce a query plan for those computations, and you will run that query in the distributed environment. Now, then you look at this, and certain primitive computations you really, really want to perform closer to the data, because you will save tremendously on the amount of I/O that is happening in the data transfer. Now, from there, if you do that, you also deliver on the concurrency of such computations. So now you can perform those computations at a highly concurrent environment where thousands of data scientists are attaching to the same data that is collected and centralized and stored in something like MemSQL. And then they're performing their computations concurrently. So you're opening up all the data to the organization and not having any data silos. So data locality for computations is useful where it makes sense, and not as useful in a broader general purpose way. And the perfect system would be engineered around pushing the computations closer to data where it makes a ton of sense. For example, you do a lot of filtering, or you're performing a lot of what is called group by operations. And those operations make sense to be done locally. Those operations make sense to be done in a vectorized fashion by leveraging the latest and greatest CPU instructions in the Intel hardware, and so on. It makes sense to leverage indexes, so you prune massive amounts of data so you don't even touch them for your computations. And then from there, it makes sense to bring all that data into a stateless distributed environment and perform the rest of the computations. So that approach allows you to build greater scalability for your system compared to a traditional database, compared to Hadoop, or compared to Spark.
Okay. And now you just mentioned the taking advantage of the instruction sets of the underlying hardware. And you guys are making an announcement with Intel at Amazon reInvent next week. Is it related to that area?
Definitely. Intel has been supporting vectorized instructions for some time, for over a decade. And every new generation of CPUs increases the size of the vector that you can use and perform vectorized operations on top of. And where we stand right now, it's 512 bits. So compared to matrices in a GPU, this is tiny. However, when you perform a last mile computation like dot product, it allows you to perform that computation much faster than the memory bandwidth that you have. So you actually don't need more for that last mile computation than AVX 512, because your limitation is not your compute. Your limitation is memory bandwidth. This is very, very different when you train models and perform computations for building deep learning. That's where you perform a lot of tensor multiplication, and the amount of compute compared to the size of your data set is tremendously more when you're performing something like dot product. That's where you want GPUs.
Okay.
But once the model is built and the model is trained, you actually don't need GPUs to score that model in many, many cases. What that gives you is it gives you the ability to democratize that computation, because Intel CPU is everywhere. If a machine has a GPU, it also has an Intel CPU. And the point that I'm making that in many cases, all you need is a CPU, and you're not going to get the computation faster if you add a GPU to the system, simply because it's the memory bandwidth that's your bottleneck in the computation. Now, we use AVX512 for vector dot product, for Euclidean distance, and for other vector operations that we built into the database. We also use AVX512 for general purpose SQL computations. And that allows you to just deliver on orders of magnitude faster SQL query processing that our competitors have, and certainly what Hadoop has or Spark. We're huge fans of that technology, and we can't wait when Intel allows us to perform computations on larger vectors, not just 512 bits.
Mm. Can you be more specific in terms of some of the actual results you've seen in production systems in terms of performance differences?
Yeah, absolutely. So with MemSQL 6.0 that we just released in October, we can do things like a group by operation on 100 billion row table in a sub-second. So
100 billion?
100 billion, yes.
Wow.
So it says a sub-second operation that runs something like give me an average stock price over 100 billion data points, and group it by security or by stock value. The computation itself is relatively straightforward, but because we perform that computation, quote unquote, on compressed data, and we're using those vectorized operations, we achieve the performance of 1 billion operations per second per core. So if you throw 100 cores into the system, and MemSQL is extremely scalable, so you can throw 100 cores or you can throw 1,000 cores, you can achieve this type of performance on your system.
And so that's using the AVX512 instructions. What were you seeing prior to that?
Well, there's a combination of two techniques that goes into this type of performance. The first is, how can you perform operations on compressed data? So if, like I said earlier, oftentimes it's the memory bandwidth that's the bottleneck of your computation. So the better you compress, but the better off you are in the final computation, because at the end of the day, you scan fewer bytes.
What exactly do we mean by compressor? Is it kind of your traditional, binary compression, or are we also talking some kind of deduplication or something like that?
It's a combination. So first of all, the compression is called column store compression. And we also encode similar values. So let's say you in that example that I said with stock trading, you have 10,000 different stocks. So if you have 10,000 different stocks, then each individual stock can be encoded with just a few bits. Right. And so then you only use this many bits to represent each stock value. And as you perform your computations, you never go back decoding those bits into, let's say, an integer value, or God forbid, a string value of a stock, right? Because those computations will become much more expensive. So now that you perform computations on compressed data, the second step that you do is you optimize your computation for as few branch mispredictions and as few cache misses as possible. And those are a big deal, because every time you have a branch misprediction, you flash your CPU pipeline. So that slows down your computation. So if you express your computation so there are no branches, basically. And there are some very, very cool papers out there, and there's some innovation that we've done here at MemSQL as well. So that will give you the second boost. And then the third boost is, now you take all those bits that you represent your values, and you perform vector operations on top of those encoded values. And then that's where you use AVX512. So now, and that gives you kind of another, I would say, 3 to 5x performance improvements just by using AVX512. But if you take that, plus you take operations on compressed data, plus you take care of branch misprediction, you multiply all those together, and then you can routinely see 2 orders of magnitude improvement in performance.
Wow. That's pretty fantastic.
Kind of the point here is, fancy hardware is cool and you want to use it where it's needed, but also there's a lot of potential in the hardware you have at hand. And if you take full advantage of that hardware, you will have remarkable results.
Mm-hmm. Oh, that's great. I guess as we kind of wrap up, do you have any additional kind of advice to folks that are looking to, get better, to take better advantage of, whether it's their data storage systems, their, hardware systems, and to use these to make better, predictions and better utilize machine learning and AI?
Well, my advice here is don't settle. There are systems out there such as MemSQL that allows you to take pretty much your end-to-end machine learning, AI, and application development pipeline and make them completely real-time. So whatever you do in batch, whatever you have to wait for, with the right technology can be squished down to zero.
Is that the technical term?
Squished to zero? So, yeah, let's say that. and that's where the world is going. So we'll live in the world in the future where compute and storage are going to be utilities. And if you're willing to pay for compute, you will have as much compute as you need at any concurrency as you need and any latency as you need. And the only thing that is going to be bounded by is the amount of money you pay for that compute.
Great. Well, Nikita, thank you so much for spending the time to chat with me. I really appreciate it.
Yeah, absolutely. Thanks for having me.
All right, everyone. That's our show for today. Thanks so much for listening and for your continued feedback and support. For more information on Nikita or any of the topics covered in this episode, head on over to twimlai.com/talk/84. To follow along with our AWS reInvent series, visit twimlai.com/reinvent. Of course, we would love to receive your feedback or questions either via a comment on the show notes page or via Twitter to @twimlai or @SamCharrington. Thanks once again to Intel Nirvana for their sponsorship of this series. To learn more about DeepLens and the other things they've been up to, visit intelnirvana.com. And thank you once again for listening, and catch you next time.